Hey guys, today I'd like to show you how to do an elasto-plastic analysis with robot structural analysis. We're going to start off by going to New Project, Frame 2D Design, and I'll go ahead and make a grid by clicking Axis Definition, Cartesian, number of repetitions, 2, 20 feet, click on Add, and then go to Z-axis, number of repetitions, 1, 20 feet, Add, and click Apply, Close. Alright, so I'll go ahead and go into bars, and I'm going to leave it as simple bar. In here, I have to change the section. So I click on the ellipses to the right of the section, and I'm going to use a W section at W12 by 16. So I'm going to go here, W12 by 16. W12 by 16. Okay, so here you have Elasto-Plastic analysis shaded out. So you go ahead and click the checkbox and click Elasto-Plastic analysis. So you can either use a perfectly plastic model or a bilinear model with straight hardening. For this tutorial, I'm only going to use perfectly plastic. This E1 over E is tantamount to tau if you're familiar with AISC, and it would depend on your material model and whether you choose reduced modulus theory, tangential modulus theory, whatever you choose. Unloading method. This, I'm not really going to go in depth into it, but I have a Word file right here with what each of those means. So elastic means when you unload the bar or the structure, it's going to follow the path that it took when it was loaded. If it's mixed, then it will follow a straight line back to some point. Or you have the others like plastic where it'll follow Young's modulus back to the zero of the y-axis. Or you have a damage theory where you can see it goes back to the origin with a straight line. Okay, so back to what we're doing. I'm going to leave the web divisions and flange divisions as 8 and 5. You can choose to discretize it more if you choose, but I'll leave it as is. Basically, they have to subdivide the cross section of the member to do the analysis. So we'll leave that as is. Click OK. Section type, I'll have to change this. Click 12 by 16, add. Okay, close. So now I'll click back in that, and I'm gonna do it up here, and then click close. So usually a robot has the default material set to just steel, which I think might be 36 KSI, they don't really say. So I'm gonna go ahead and change that to A992 50 KSI steel. I'll come in here and get some supports. I don't think fix is in there, so I'll go ahead and delete that and make some new ones. So I'm gonna just use a pin connection. Pin UX. Close. Okay, so a pin connection right here and there. Alright, so now I'm gonna go ahead and define the loads. So load types, I'm gonna click add and then delete it so I neglect the self weight of the beam because I'm not trying to have that in there. I'm gonna just click add again, and now we have that. So I'll click here, bar force, and for this I'll use -1 kip since it's a fairly regular thing. I don't want to use some random number. Click add, and then there. If you want to see the load, you click on this button down here, load symbols, and the load value description is right next to it. So I have a straight bar 20 feet long with 1 kip force going downwards on it. So we click here into analysis parameters or analysis types, same thing. Change analysis type, statics, that's okay. And then we choose nonlinear analysis. and go to the parameters. So in here you have like the load increment number, maximum iteration number. Don't worry about that. Here we're going to want to click save results after each increment. I'll tell you why that is later. And then also additional criteria to stop analysis. So here's the two things that you would most likely use, or three things: plasticity state, reaching plasticity rate, and structural collapse. So the plasticity state, the analysis would stop once the first plastic hinge forms. Structural collapse would stop the analysis once the structure becomes a mechanism. And reaching plasticity rate, you would determine the rate. It talks about how plastic the structure is at a specific cross section. So you can change it based on that. So for this simple one that I drew right here, the plasticity state and the structure collapse are going to happen at the same time. So I'll choose plasticity state. Increment of load parameter. This is with respect to the load you chose. So because I chose one kip, it's gonna split that up based on that. Okay, so click OK. Okay, have I forgotten anything? I don't think so. Do calculations and then close. Okay, so now let's analyze our results. So for example, let's see our reactions. We have a total reactionary force of 14.6 kips. And here's what I also wanted to show you guys. So I did a simple plastic analysis using the virtual work method or kinematic method with my Young's modulus of 29,000, Fy of 50 ksi, my length of 20 feet, Zx plastic section modulus of 20.1, and I found that the plastic moment was 83.75 kip feet and the plastic limit load would be 16.75. So you might say, how am I getting 14.6? Well, the reason for that is that the kinematic method doesn't account for the yielding of, it only accounts for, it's completely elastic up to a point, then it becomes perfectly rigid. And so it doesn't account for the yielding along the cross section. The robot, however, does account for the yielding along the cross section. Also for this point, let me say in tools, job preferences, you have structural analyses, nonlinear analysis, division of elements for elasto-plastic analysis. This is automatic. So robot chooses how much elements to split how many elements to split the member into, and that would be very difficult to do by hand. Okay, so we're going to say that the plastic limit load for this beam is 14.6 kips. If we were, however, to analysis types and go to parameters, additional. If we change the load parameter to a smaller number like 0.1 or 0.01, we would probably get, not we would probably, we would get a smaller number. It just depends on how much they round it, so you would be able to see it right here. So just to let you guys know that. Cancel, close. The other way you can view your results, you can go onto maps on bars, and this window pops up. And you can do the regular stuff like what's my moment. You can see a map on the bar. You can go to design and you can say plastic ratio and click apply. Sometimes it doesn't work when you click apply to see it in this window. So if that doesn't work, then open in a new window with the scale displayed and it should be okay. So what does the scale mean? Click here to scale and you can see what it means. So um, this is the plastic ratio. So if it's red, then it's above 0.298, and if it's and so forth. You guys can understand. So I'll go ahead and take this off and click apply. Okay, so the reason I told you to check save, let me just go back to it. Parameters. Oh, the reason I told you to check save results after each increment is so that we'll be able to see the following. So if you go to loads and select case component, you're able to see how the member reacts in every load increment. So let's say, for example, we turned on the deflection. You can see what the deflection is at every load increment. And if we were to analyze this beam while it's still in the elastic range, then we should get, using like simple elastic theory, and we should be getting the same exact number. Back to my mathcad file. So robot says the maximum deflection is 1.414, and does that make sense? So using kinematic theory, the maximum deflection would be 1.615, which is incorrect because it assumes the plastic hinge is at 1 point. It's a zero length plastic hinge and it's perfectly rigid. It causes perfect rigidity throughout the rest of the member. So that's slightly incorrect. The max elastic deflection based on M over EI would be 1.374. So our value of 1.4144 makes sense. If you wanted to get a more accurate number, you could choose curvature and work it out with and modify the moment of inertia and do iterations until you get the deflections at certain times during the loading process. So also another reason you wanted to save the results was if you go to results, advanced, and diagrams, we can come here and advanced analysis function definition. We click add. I'll go ahead and say increment time. We'll add that. And then I'll go to bars or beams. Click on MY. You can choose any one of them. I'm just going to choose a moment right here at 0.5. That's the relative distance along the member. And click member 1 and click add. So now on the x-axis I'll put increment and on the y-axis I'll put the moment. And I'll click apply, open a new window. And here you can see the moment at the half point at certain times during the loading process. So I'll go ahead and close this and close this. Let's say we were to change this model and say delete. Let's create fix everything. Okay, so everything's fixed now. I just created a fix support. Click add, close, and then bam. So we'll go ahead and run this analysis again and see what happens. So since this is a fixed support and this is a roller, we would expect the I'm losing my train of thought. We would expect the plastic region. We would expect the beam to plastify at the fixed support first, and then plastify at the middle. If you look, because the higher moment will be over here, and then the next higher moment will be here. But I'm not seeing the second um, plastic region. I'm not seeing what it needs to collapse. But here we can see uh, reactions. We know that it took a 19.6 kip force to cause this, to cause the plastic, to cause that portion of the beam to plastify. So let's say now I want to see the entire thing for structural collapse to see what it would be. So we go to analysis types, parameters, additional criteria and stuff. And I'll change this to structural collapse instead of plasticity state. And press OK. OK. Calculations. No convergence of nonlinear problem. That means the structure collapsed. So do I want to continue? No. See, now you can see that you can see the plastic regions that plastified, both at the fixed support and where the load is. But it's a little bit off center, which is expected. So I'll go ahead and do one more thing. I'll go ahead and delete these just to show you. And I will put another bar here. It looks like they have disappeared. No, they haven't. They're still here. So I don't like to see the pictures. I'll just do pinned. Now go ahead and put another load on one of these bars. Let's say this is 0. Let's call that 2. Add 2. So now we'll be able to see how this reacts. Nope. Results, maps on bars, design, plastic ratio, apply. So now you're able to see where the plastic hinges form. So plastic hinge would form at here and here. So this is a very useful tool in robot structural analysis. Other simpler programs you can use to check your work would be like Mastan or one of those. I know ANSYS should be able to do it as well, and those other ones. But here it was quick, easy, and dirty. We just got through a simple plastic analysis, and you can check these by hand by using kinematic method or event-to-event analysis or equilibrium, and you should get the same answer. Well, thank you guys for watching this video. Don't forget to like, subscribe, comment, share, and again, thank you all for watching. Have a good one.